this lecture, we will study about optically active molecules. What are optically active molecules and why they are optically active? Let's see this experiment first. So, in this experiment, you have a sample of optically active molecule right here, and there is light passing through this sample. And the light has been polarized by this polarizer. This blue thing here is a polarizer. So previously the light was oscillating in all possible directions, and then now it's vibrating in just one plane. And then when it passes through the sample, the plane of the polarized light has been rotated. So the molecules which can do this is they are called optically active molecules. So the molecules here are optically active. What makes them optically active is can be answered by a thought experiment which I have tried to create here. So suppose there was a mirror in the laboratory where this experiment is happening, and inside the mirror the experiment looks like this. If for some time you can imagine the world inside the mirror to be real, then you can understand why these molecules were optically active. So inside the mirror, when you see the same experiment is happening, the light is plane polarized, and then now the light has been rotated in opposite sense as compared to what was happening in the laboratory. So here, if you see the rotation was anti-clockwise, then here the rotation is clockwise, right? What is the difference between these two experiments? Let's not go into the virtuality and reality of this experience. Just think about the molecules. So then you can see the molecules in both these experiments are mirror images of each other. And because they are behaving differently with light, it means that these molecules here should be different than these molecules. They are mirror images and they should be non-superimposable with these molecules, which means that these molecules should be chiral. If you haven't seen my lecture on chirality, then I will post a link in the description so that you can watch that video in which I have explained what are chiral objects. So these molecules must be chiral. So optically active molecules have non-superimposable mirror image, which is the definition of chirality also. A chiral object have non-superimposable mirror image. So optically active molecules should be chiral, right? So for people who have already known that some carbons are chiral and there are some chiral centers in the molecule. I'm not talking about a particular center in the molecule which is chiral. I am just talking about the whole molecule. So you have to see if the whole molecule is chiral or not. Okay, it's very different from saying that it has a chiral carbon or something like that, if you have heard about those things. The molecule must be chiral overall. So let's take an example. Are water molecules chiral, which means is water an optically active compound? Water would be an optically active compound only if its molecules are chiral, as we saw in the thought experiment. So water molecule looks like this. You need an exact representation of the water molecule. You can't just go by the structure. So it's a bent shape. Water molecule has a bent shape. And if you take a mirror in front of this molecule and you take a mirror image, you can see that these two mirror images are superimposable. That's why they are not different, and the water molecules are not chiral, right? So water cannot rotate the plane of polarized light. Okay, so we don't have to check these molecules again and again for chirality, but for students who are going through it for the first time, it's very much recommended. So let's begin. I can generalize one thing here, that there can be no chirality in molecules with 1D or 2D geometry. So suppose you have a linear molecule like this. Then if you take a mirror and you take the mirror image, you can obviously see that they are superimposable and this molecule is not chiral. Even if both the sides, both the attachments of the molecule was different, then again if you can take the mirror image and like at the first sight you can say that this is non-superimposable, but if you rotate it like this, then it gets superimposable, right? So this is also not a chiral molecule. So linear molecules cannot be chiral. I've taken both the examples, symmetric and unsymmetric. And then let's move on to planar geometry. So we have a trigonal planar geometry. Some molecules are trigonal planar. In that geometry, if you have all the attachments same, then of course you won't get any chirality because the mirror image will definitely be superimposable. Suppose one of the attachment is different, like I've shown here, the green sphere is different from the blue sphere. And then you take the mirror image, then again you see that this is superimposable and this is not chiral. So what I am proposing is that there can be no chirality in 1D and 2D geometry. Let's take more examples. What if all the three attachments of a trigonal planar molecule were different? Then you take a mirror image and you get something like this. So you might get confused if you think of a rotation like this. Suppose you have the axis which is going through this red atom and through the plane, and if you rotate it like this, like a fan which rotates. Suppose these are the wings of a fan, and you rotate it like this and try to superimpose. Then first you bring the black one up, and then the green one is here and the blue one is here like this, and then you see that it is not superimposable with the first molecule. Okay, then you can rotate more, and then again the black is here. So the black is here, but the blue part of the molecule, this blue sphere is up. So you're rotating it like a fan. So the blue is here and the green is here. And then you can say that this is not getting superimposed with the first one and it could be chiral. But wait a minute, what if you try this kind of a rotation? So think about this axis which passes through the green sphere and the red sphere, and you rotate it, like flip it. And then you can see if you flip it, the blue one is here and the black one is here, and then this is superimposable, right? So this molecule is also not chiral. So if you didn't notice, a very interesting thing which happened here is like we used the third dimension of space to make this molecule superimposable, because when we were flipping this molecule like this, we were using the depth of the space. If you do rotation in 2 dimension only, you won't be able to superimpose it, but our world, the space around us, is 3D perhaps. So then this is the key move. No matter how unsymmetric a molecule is in 2D, then you can always take the mirror image and flip it like this to make it superimposable. This is the key move here. Okay. So because this was possible because of the third dimension of the space. Okay, so we still don't have chirality with planar structure. Now let's think about what about square planar geometry. So I will demonstrate only the most unsymmetric kind of molecule with all the 4 attachments different, and then I can take a mirror image and then I can flip it using the third dimension of the space like this, and I will flip it and the green will go here and the blue will go here and the orange will come from the back side here and the black will come here, and you can see now that they are superimposable, right? So not chiral, right? So this way I can prove you, because of this move, this special move which we have using the third dimension of space, you can understand that there can be no chirality in a linear or a planar geometry. Okay, chirality is thus possible only with molecular shapes which extend in all the 3 dimensions of space. So those shapes are tetrahedral, this shape, trigonal bipyramidal, and octahedral. These are the common shapes. Then there can be more shapes like this which extend in 3 dimensions. There can be more molecular shapes, but these are the common ones. So let's check with the tetrahedral. First of all, I would like you all to see what a tetrahedral shape looks like. Can you feel it? Just see it rotating. So it has 4 attachments and all of them are equally spaced. This is a very beautiful shape. This is a quite a symmetric shape, right? Okay. So now In tetrahedral shape, if you analyze, then you will figure out that in tetrahedral shape, chirality will arise only if all the four groups attached to the central atom are different. For example, if we have all the four groups which are same, then I can take a mirror image like this, and at the first sight you will see that it's not superimposable. I have used something special here, like this is a solid bond which is like coming towards you, and this is a dashed bond which is going like away from you inside the screen, you can imagine, and this is like coming outside the screen. And then you take a mirror image, and you see this thing which is coming towards you, it has a mirror image which is coming towards you in this direction. So the mirror image has been properly taken, and now we see that these are not superimposable. But if we take an axis like this and rotate it, because the two connections which are in the plane of the screen are here, and the two connections here which are in the plane of the screen are like this. So if I rotate it, then this sphere will go to that side, and these two will adjust themselves in a way which is very obvious. This will come like this will go one, we are doing a 180-degree rotation here, right? So this thing is coming all the way from back side to here, let's say. So this will go all the way to back, like here. This sphere is here, and this thing will come all the way 180 degrees rotated to front side here, and now you can see that they are superimposable. It was pretty easy though, but still I gave all the like I superimposed it very properly, because this is a very intricate issue, chirality, so you have to check superimposability carefully. So they are, of course they are superimposable, and we haven't yet achieved chirality in tetrahedral shape. So my hypothesis is that in the tetrahedral shape it will arise only if all the four groups are different. Okay, let's see what's the next one. So now we have three different groups, and the green is repeated. What about this? If I take a mirror image, I make a mirror image, and then I try to superimpose, and I can bring this orange sphere here, this side, by 180-degree rotation, and you will see that the green will adjust themselves just fine, and they are again superimposable. So you see, with three different groups we don't have chirality yet. Only if all the four groups are different in tetrahedral shape, then we will get chirality. Now I can demonstrate that to you. Now we have all the four groups which are different. I take a mirror image, take a look at it properly, then I rotate to bring this orange here, and the black which was on the back side, it rotates 180 degrees and comes in the front, and the green, it rotates 180 degree and goes that side. And now you can see that they are not superimposable, right? The blue is at the top, the orange is at the right, but these two groups are not getting superimposed. And you can try as many moves as you like, you would never be able to superimpose these two molecules. So this is the mirror image molecule of this molecule, and that's not superimposable on the first one. That's why we have non-superimposable mirror image of a molecule, and that's why this molecule is chiral, or this molecule is also chiral in that way, because mirror image is a symmetric relation. Okay, how about in trigonal bipyramidal shape? When all the five connections are different, there will be chirality. I will show it to you right here. Suppose this is a trigonal bipyramidal shape. So why it is called trigonal bipyramidal, I expect my viewers to know it, but if they don't know it, then you see this is a triangle, and then there are two pyramids on the upside and the downside. So this is trigonal bipyramidal shape, and in this shape, if we have all the five groups attached to the central atom which are different than each other, then if you take a mirror image of this molecule, you get this. And if you want to superimpose them, to superimpose them, I would like to have this yellow here to come to here, right? So I will rotate it a little bit, then the blue will go on the back side, and this thing will come in the like straight here, right? And now we see that they are not superimposable because the black is there, the blue is sorry, the green is superimposed, right? And we also superimposed which one, the yellow one. The yellow is superimposed, but these two, orange and blue, are not getting superimposed. So that's why the whole molecule has a mirror image which is not superimposable with the molecule itself. That's why we have chirality here also in this geometry. Okay, your mind must be thinking about some other things. I will put up that question very soon. I'm just trying to show you that chirality can arise in only those molecules which extend in all the three dimensions of the space. And then now we have an octahedral shape in which if I take all the six connections different, then you will see again there will be chirality. Take a mirror, you take a mirror image, and of course I will not like to move this green and the blue one. I will try to superimpose other ones because they are already superimposed here. The green is at the top and the blue is at the bottom. And if I rotate, let's see which one I was trying to superimpose. I rotated this and the yellow one is here and the pink one goes there and the black one goes on the back side and the orange comes here like that. No, sorry, I have rotated it like this. The yellow goes here and the orange is here and the black is here and the pink is there. And at this position now you can see that this are superimposed, blue is superimposed, black and black, they are superimposed. But the other three groups, yellow is also superimposed, but these two here, they are not getting superimposed. So the whole molecule has a non-superimposable mirror image, and there is chirality in octahedral shape also, right? Perfect. So this is a question for the viewers. I will post a video explaining the answer very soon, but this is for the viewers to decide how can you achieve chirality in trigonal, bipyramidal and octahedral shape with least kind of different connections. Because what we saw that if there is a central atom and you have 5 different groups in trigonal bipyramidal geometry, then we achieved chirality. And if we had 6 different groups in the octahedral shape, then we had chirality again. But how can you minimize this situation? How can you have the least number of different kind of connections and achieve chirality in both these geometries, right? For example, you can think about, suppose this is atom A and then this is B and this is B and this is B and this is C and this is C. So I am using only two kind of connections, B's and C's. So I am using only B and C, and if is this chiral or not, so you will have to think like this. And what is the answer? I would like the viewers to comment and explore for their own. Thank you very much for watching the video. No, okay, sorry, there is one more question here for students who are preparing for JEE mains examination, which is an examination for engineering entrance into engineering colleges in India. So but this question here is very easy. The number of possible optical isomers for the complexes Ma2B2 with sp3 and dsp2 hybridized metal atom. So this is your central metal atom, and if it is sp3, then it has a tetrahedral geometry, and you have these attachments A and B, and you cannot achieve chirality here, right? So optical isomers are not possible, right? because you can't get two different kind of molecules here which will rotate the plane of polarized light differently, because any molecule you make like this will be same, will be superimposable. Even if you like attach A here and A here and B on the top and B here, then you can rotate this molecule and you can superimpose it with this one because they are the same. Chirality appears in tetrahedral geometry only if all the four attachments are different. And similarly, in the second hybridization, DSP2 leads to a square planar geometry. I, I hope my viewers know about this. So square planar geometry, in square planar geometry, even if with four different groups, four different attachments, we can't have optical isomers. So that's why the answer is 0 and 0. Thank you very much for watching the video.